Yo, what's up, guys? Back again. Doing some probability and statistics. This assignment. Keep it rolling. Do the next problem. Let's see. All right, is this still working? Pen? Dang, like this pen isn't working again. I guess I gotta like do this every time. Remove it. What do I have to do? Restore it? No. Wait, is this working now? Yeah, it's working. Okay. Yeah, I had to remove it, restore it. I guess just the pen settings. Yeah, okay, it takes a minute to load. The pen. Screen area, monitor 2. Boom. All right. Let's fucking go. All right. Let's see. Let's look at problem 2 here. All right. Alice plays with Bob the following game. Alice randomly chooses 4 cards out of 52. Memorizes them, places them back into the card deck. Bob randomly chooses 8 cards. Alice wins. Okay. So first it was like Alice. So I guess you have like these cards. And Alice does something and then kind of puts them back. And then like Bob does something. Does like something with 4. Bob does something with 8. Alice wins if Bob. Okay, so Alice 4 cards. So it's kind of like Alice kind of has like the 52 cards. She kind of picks 4. She chooses 4, memorizes them, and places them. So it's almost like, I don't know, she chooses these 4. Kind of need some more of that. Yeah. Okay. I don't know. For some reason, I just really want to like draw this out even more explicitly. So we kind of start off with like these 52, and then kind of as the result of this process, it's like the same 52. But Alice like chose 4 of them. Those 4. Okay. I don't know. Yeah. I don't know how explicit I'm going to do this, but I'm just going to like keep going. It's like, okay, so we start with like the 52. And then we have like 52. Okay. We have like, now we have like 52 minus 4 in here. And we have like 1, 2, 3, 4. Alice kind of like chooses 4 of these. Okay. Then she puts them back into the deck. Like this. So we're like back up to 52. And we'll say maybe like a little portion of them is maybe we could like draw it a little bit, like 1, 2, 3, and 4. Like 4 of them are in there. And Bob randomly chooses 8 cards. So this is kind of like Alice does this. And then Bob chooses 8 cards. So there's like 52 minus 8 left in here. And Bob chooses 8. 2, 3, 4, 5, 6, 7, 8. And so, I don't know, let's say he chooses like 8 and like 2 of them are Alice's cards. So Alice wins if Bob's cards include all cards selected by her. Okay. What's the probability of this happening? Okay. Bob. So at this point, we have like 4 out of the 52 cards is Alice's. And then Bob randomly chooses 8 cards out of the same deck. Alice wins if Bob's cards. What is the probability of this happening? What is the probability of Alice winning? So it's like, I don't know. It would be like, we can almost think of like a simplified problem. Like what if Bob only picked 4 cards? Then what is the probability of Alice winning? Bob picks all 4 cards. It's like, in order for Alice to win, Bob, with every single pick, has to pick Alice's card. So the probability of that happening first is 4 out of 52. And then, like, he has to pick another card. So there's like a 3 out of 52 chance of that happening. Then like a 2 out of 52 chance. Then like a 1 out of 52 chance. It's like, imagine if he gets like, oh my God, imagine in real life, it's like Alice is trying to win. It's like so unlikely that Bob picks like the first card, but it's like, oh shit, like it's like, oh, okay, all right, cool. Like we got 1 card. And then we're like, all right, it's like, oh my God, it's like a 2% chance we're going to pick this next one, but we like pick it. And we're like, oh, dang. All right. Now, like, something's going. But, like, it's like to get this far is, like, so unlikely. I mean, this is, like, 2%. And then, like, 2% of 2%. So, oh, my God. And then we get this. And we're like, oh, my God. What? Like, what? We got 3? Like, this is crazy. But like, there's such a small chance. Just like it's almost never gonna happen that like Bob picks like Alice's last card, and then like imagine if that just fucking like turned up Alice's card, it'd just be like, oh my God, oh, it's like so crazy, just absolutely nuts. So, yeah. So this would this would be the probability of Alice winning if Bob just picked 4 cards. That's it. What if we just added a 5th card? then it's like, it's almost like Alice could do this. She could Bob could do this. Like the first card is bad, but then like the next 4 cards are good. Or like the first card is good, or like the second card is bad, or like the third card is bad, or the fourth card is bad, or the fifth card is bad. So just looking at these, do all of these have the same probability? Like this one, let's just take x 1, 2, 3, 4. Like, so the probability of this happening. So we have 52 cards, and let's pick one that's not Alice's. So there's a 48 out of 52 chance of that happening. Now let's pick one of Alice's. 4 over 51 times 3 over 50 times 2 over 49 times 1 out of 48. Okay, so that's that. What about this one? Like yes, no, no. Yes, no, yes, yes, yes. So this is 4 out of 52 times, all right, this would be 47. Yeah, this is a little bit different. Times 47 out of 51 times, so the next one is yes. 3 over 50 times 2 over 49 times 1 over 48. Okay, and just to do one more, let's do yes, yes, no, yes, yes. So this would be 4 over 52 times 3 over 51 times, so 48, 47, 46. 46 over 50 times 2 over 49 is 1 over 48. Any patterns jumping out? So there's always 4 times 3 times 2 times 1 up here. And there's always 52 times 51 times 50 times 49 times 48. The only thing that differs is like every time, depending on the card position, there's 48 or 47 or 46, or there would be 45 over here, or there would be 44. So I'm almost kind of thinking that, well, it's because like, so the probability is like slightly different every time. So kind of adding up the probability seems kind of hairy. The question one might ask is, if this is a counting problem, which it is, it's, I mean, each outcome is not equally likely. Like this is not equally likely as this, is this, is this, is this. Intuitively, does that make sense though? Like, which one of these is most likely? Like, it's actually not clear which one would be most likely. Like is this one most likely, or is this one most likely to get all the 4 cards out of the way first? And then, I mean, certainly by the time you get to this point, it's like, you'd much rather like be in this position, like trying to hit this versus like in this position. You'd much rather be in this position trying to hit this versus like being in this position and trying to hit this. Like, oh my God, this is like so okay, this is guaranteed. I mean, this is like 100% that this is gonna happen. Versus like this is like, oh my God, that's very unlikely. So let's go back to the problem. Like Alice plays with Bob, chooses 8 cards. I mean, this just seems like it's going to be hairy. I mean, this is just a standalone problem. So like I mean, if you think in terms of like the problem's weights, I mean, this is 1 and this one 2. This one has freaking 5 parts. And this one only has 1. So you wouldn't like maybe this one has, I mean, this one has 2 parts. This one has 2 parts. So like this one should maybe be hairy. Can we I don't even think we can. You can only do the counting problem. You can only make it a counting problem when all those probabilities are the same. And I mean, you started off as a counting problem in the sense where, you know, any 8 cards that you pick, like those cards are all going to be equally likely. Okay. Now we're getting somewhere. So all those 8 cards are going to be equally likely. So we just look at like all possible 8 cards, and then we just see like how many of those is like the Alice winning condition. And so we just divide by that. So dang, okay, nice. So that's how this becomes a counting problem. So how many different 8 card things are there? There's 52 times 51 times 50 times 49. 7. So this is card 1, 2, 3, 4, 5, 6, 46. There's 45. So this is how many 8 card things there are. There's like 52 for the first card, 51 for the next, blah, blah, blah. Okay, so cool. So I don't know, we could call this like N or something. This is maybe C or something. This is how many possible things there are. I don't know. And so now we want to see under how many ways of like in here can Alice win. I think you just want to choose 4 of these. It's just like 8 choose 4. I mean, that would be the most intuitive. 8 choose 4. So you have 8 things and you want to choose 4 of them. So you have like 8 things, like 1, 2. Let me go. Running out of battery. Let me plug in my thing. All right, we good. All right, so now it's like, yeah, it was like we have 8 things and we choose 4 of them. So we basically want to say like, oh, we want to choose 4. So like 1, 6, 2, 7. Like that's 4 of them. It's like how many 4 element sets can we make from 8 things? Well, to generate this set, it's kind of like a sequential decision process. It's like, what's the first element going to be? What's the second? What's the third? What's the fourth? So the first element, we basically have like 8 choices. The second element, we have 7. Next one, we have 6. Next one, we have 5. So is it basically just n factorial over n minus m factorial? Is that it? Oh, but you don't want to double count things. Like you don't want to double count you know, like 6, 2, 1, 7. So you additionally divide by the number of ways to permute this. So it's like times m factorial. Yeah, cool. So yeah, so let's say the probability of Alice winning is the number of kind of like winning hands over the total number of hands. So this is literally just 8 choose 4. Whoops. This is 8 choose 4 for n, which is equal to I think we just said it was n factorial over m factorial times n minus m. So this is also 4 factorial. And this is divided by n, which is basically 52 factorial divided by 44 factorial, which is equal to 8 factorial over 4 factorial times 4 factorial times 44 factorial over 52 factorial, which is equal to okay, so these all cancel out here. Well, I mean, we just like wrote it like this. So this is just, I'm gonna write kind of like weird notation, but it's like times 1 over 52 to 45 factorial. Not even factorial. It's just, I guess if you wanted to write it even more simple, it's like 52 times 51 times all the way up to down to 45. Any way to simplify this? Yeah, you could, but I don't know. I think we can just like do it out with the calculator at this point. So 8 factorial. So if we have like 8 factorial divided by 4 factorial times 4 factorial times 1 over 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45 should be it. Blah, 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 something to the negative 12th. All right, let's see if that's right. Oh, cool. You don't actually need to like write it out. I'll kind of, oh, wait, sorry. Have the thing down here. So you just said 4 choose 4 over blah, blah, blah. So can we write this out in terms of choosing stuff? So 8 choose 4, blah, blah, whatever. He's writing this out in terms of like choose. So let's just see what he did. So since 4 cards are fixed, Bob can only choose 4 more cards out of the remaining 48 cards. Total number of hands. I don't understand this. Like, since 4 cards are fixed, Bob can only choose. Okay. Okay. So it's kind of thinking like Bob is choosing 8 cards and you have to fix 4 of them. You're not sure which 4 you're fixing, but okay. Total number of hands Bob can have such that they include Alice's cards is 48 choose 4. That's weird to think about. I don't fully grok that. Choose any 8 cards. Like, that's fine. So this numerator is essentially this is the number of hands where Alice wins. So kind of working backwards from that, it's like the way that I calculated that was I just said it was 8 choose 4. That's different from 4 choose 4 times 48 choose 4. All right, my brain's getting kind of fried. I think I might be done. I think I might have to leave this, kind of come back to it. I think that might kind of be it. All right. Thanks, guys. I will plan on coming back to this and see you later. Peace.